Welcome to the 29th lecture in this open course on diffusion in multi-component solids. In this lecture, I have explained three experimental techniques which are commonly used for measurements of vacancy concentrations or the enthalpy of vacancy formation. These techniques include differential dilatometry, residual resistivity, and positron annihilation. In the last class, we discussed the energetics of vacancy formation, and in this lecture we will go over some of the experimental techniques which are used for measurement of vacancy concentration or enthalpy of vacancy formation. So, just quickly a refresher, you got the expression for mono vacancy concentration x1v as exponential delta S1v vibrational divided by k times exponential minus delta H1v divided by kt, where delta S1v vibrational denotes the vibrational entropy change associated with the formation of a mono vacancy, and delta H1v denotes the enthalpy of formation of a mono vacancy. K is the Boltzmann constant and T is the temperature in Kelvin. Now, it should be noted, when we use these quantities delta H and delta S in terms of per mole, then we need to replace K with the gas constant R. Now, let us go over some of the techniques which can be used for measurement of these various parameters x1v or delta H1v. The first of this technique is called differential dilatometry or DD in short. So, this technique relies upon the measurement of volume change that any metal piece undergoes upon heating. So, when a metal piece is heated, it experiences expansion, and this expansion has mainly two contributions. The first one is purely from the thermal expansion, and the second one is because of the formation of vacancies. As we have seen, the vacancy concentration varies exponentially with temperature, which is clear from this equation. As the temperature increases, vacancy concentration increases exponentially, and the way the vacancies are formed, which we have seen last class, introduction of a vacancy gives rise to one additional lattice site into the crystal, and so as the temperature increases, to maintain the equilibrium, extra vacancies are formed, and so the extra lattice sites are added to the crystal structure. This will give rise to the second contribution to the net volume change, which is caused upon heating. If we can measure this volume change and the individual contribution, we can relate them to the vacancy concentration, and that is the principle here. So, let us say if the piece of a metal is heated from a lower temperature T0 to a higher temperature T, it undergoes the change in volume equal to delta V. So, let us denote the volumes at T0 and T by V0 and V. The lattice parameter at T0 and T are denoted by A0 and A. Then let us consider the volume per lattice site, which is denoted by omega. So, omega 0 and omega denote the volume per lattice site at the two respective temperatures. and let us suppose at t 0 there were big N number of lattice sites, and as we heated to T, because of the extra vacancies which have to be created to maintain the equilibrium vacancy concentration at T, there are N vacancies which have been added. So, small n is the extra vacancies at T over those at T 0. So, delta V is simply V minus V 0, and at T 0 volume per lattice site was omega 0. There were n total number of lattice sites, and at T the volume per lattice site was omega, and there were total number of n plus n sites. So, we can write this as n plus n times omega minus big N times omega 0. So, if we take this capital N common, we get n times omega minus omega 0 plus small n times omega. And if we denote this omega minus omega 0 as delta omega, we get delta V equal to n delta omega plus small n times omega. Now, we have clearly got the two different parts. So, delta omega is basically the change in volume per lattice site. And as you can understand, this is purely because of thermal expansion. Now, when we say that, we are also making one assumption here, and that assumption is that there is no change in volume per lattice site because of creation of extra vacancies. Okay. So, what we are assuming is that at any given temperature T, if a vacancy is created, there is one extra lattice site which is added, and that extra lattice site also has the volume omega, or the creation of the vacancy does not change the volume per lattice site. Now, in practice there may be a little bit of change in volume because of creation of the vacancies. Right. So, to understand this, if we consider a lattice with a vacancy, and as we have seen, the atoms are held at their equilibrium positions because of the balanced interactions. At the equilibrium positions, the interactions are balanced, and so the atoms stay at their equilibrium positions. In fact, they keep vibrating about the equilibrium positions. But when a site is vacant, locally the interactions are not balanced, and so the surrounding atoms will tend to fall into this vacant site. So, that will give rise to some change in the volume because of creation of a vacancy. So, these atomic rearrangements will cause some change in volume, but that change in volume per lattice site will be negligible. So, we can neglect that. So, now if we divide both the side of this equation by the original volume V 0 n delta omega over, and V 0 is nothing but n times omega 0 plus n over n times omega over omega 0. This n will get cancelled. So, we can write now again in this equation the small n over big N, we can approximately make it equal to x 1 v, that is the equilibrium concentration of vacancies at temperature T. This is because the temperature T0 is usually selected at a very low value and the temperature T is at a very high value, because of which the vacancy concentration at T is much higher than that at T0. So, the change in vacancy concentration is approximately equal to the new vacancy concentration established at temperature T, and so we can approximately take this equal to x 1 v, and also the change in volume per lattice side is also not significant. So, omega is approximately equal to omega 0, or omega over omega 0 is approximately equal to 1. So, if we rearrange, we get x 1 v equal to delta v over v 0 minus delta omega over omega 0. Now, the linear dimensions are easiest to measure. So, we can relate this delta v by v 0 or delta omega by omega 0 to the linear dimensions, and typically the relative change in volume is equal to approximately 3 times the relative change in linear dimensions. So, when we talk about the piece of metal, delta v by v 0 is equal to 3 times delta L over L 0, where delta L is the change in length because of heating from T 0 to T, and L 0 is the original length of the metal piece at T 0. What can be said about delta omega over omega 0? Right. So, the omega refers to the volume per lattice side, and when it comes to the lattice, the linear dimension we can take as the lattice parameter. So, delta omega by omega 0 is equal to 3 times delta A by A 0, where delta A is the change in lattice parameter because of the heating from T 0 to T, and A 0 is the lattice parameter of the metal piece at T 0. So, we can write this as x 1 v is equal to 3 times delta L over L 0 minus delta A over A 0. So, this gives us an idea about how we can go about measuring the vacancy concentrations by measuring the linear dimensions. So, if we can measure delta L by L 0 for the overall metal piece and delta A by A 0, which are the changes in lattice parameter, then we can measure the vacancy concentration at the given temperature T. So, how do we go about this? Obviously, we need to make measurements of lattice parameters. So, we need to use X-ray diffractometer, and typically there are dedicated X-ray diffractometers which are equipped with measurement of small changes in linear dimensions of the metal piece. At the same time, the change in lattice parameter is tracked and they are related to the vacancy concentration. Of course, we also need the XRD to be equipped with high temperature measurements, so that we can do the measurements at different temperatures. This is an equilibrium measurement technique, which means that at every temperature before the measurement we equilibrate the sample, so that the equilibrium vacancy concentration at that temperature is established. And to make sure that we are measuring the equilibrium vacancy concentrations, typically the measurements are done during heating as well as during cooling. Every time before the measurement at the given temperature, the sample is equilibrated, so that the equilibrium vacancy concentration is established. Now, it looks very simple, but in fact the measurements are very critical. We need very high accuracy and precision. Why? Because the values of x 1 v, the equilibrium vacancy concentrations are typically very small. Even close to melting temperature, x 1 v is typically about 10 to power minus 4, which means if we expect about 10% accuracy, we need to measure delta L by L 0 and delta A by A 0 with accuracy of 10 to power minus 5. That is when we have a very high vacancy concentration, about 10 to power minus 4, right. So, the measurements have to be done with very high accuracy. Now, one advantage of this method is that it gives the absolute concentration of vacancies x 1 v, and since x 1 v is equal to exponential delta S 1 v vibrational by k times exponential minus delta H 1 v by k t. If we do the measurements at different temperatures, it also helps in evaluating delta H 1 v as well as delta S 1 v. So, if we take log on both sides, ln x 1 v should be equal to minus delta H 1 v by k times 1 by t plus delta S 1 v vibrational by k. So, if we plot the log of vacancy concentration as a function of reciprocal of temperature, we should be able to put the data with a straight line. The slope of it will yield the value of delta H 1 v. So, the slope would be equal to minus delta H 1 v by k, and the intercept will give the value of delta S 1 v vibrational. Now, the intercept is at 1 by t equal to 0, which is not possible, right. So, we have to just do the extrapolation of the data that we have obtained to the 1 by t equal to 0 axis to get to delta S 1 v vibrational, that is the vibrational entropy change due to formation of a monovacancy. There is one more point has to be noted here. When we do these measurements, we are talking about monovacancies, but it should be noted that these measurements do not separate the monovacancies or divacancies or other higher clusters of vacancies. It just measures the vacancy concentration. Okay. But typically we can take it as monovacancies because the divacancy concentration will be much lesser. As we have seen last class, even at near to melting temperature for platinum, the divacancy concentration was about 3 orders of magnitude lower than the monovacancy concentration. So, the error in monovacancy concentration involved is much lower, even if we assume that the entire vacancy concentration belongs to the monovacancies. So, let us look into some results from the literature. Here I am showing the results from the classic work reported by Simmons and Baluffi on the measurement of equilibrium vacancy concentration in gold using the differential dilatometry technique. This plot is the plot of delta L by L or delta A by A versus temperature, and this is in the smaller range of temperature from room temperature to 600 degrees Celsius. Now, they have reported the measurement accuracy of about 10 to power minus 5 in the measurements of delta L by L or delta A by A, and in this temperature range up to 600 degrees centigrade, the changes in vacancy concentration is not significant. So, the changes in this delta L by L or delta A by A were not in the detectable limit, and so you can see all these measurements overlap in this temperature range. But at higher temperature range 900 to 1050 degrees centigrade, you can see the difference between delta L by L and delta A by A is detectable. Delta L by L is of course higher than delta A by A, and the difference is increasing with increasing temperature. So, then plotted in this temperature range 900 to 1050 degrees centigrade, x 1 v versus 1 by T, and they could get the enthalpy of vacancy formation and vibrational entropy of vacancy formation, and the values they obtained were delta H 1 v of 0.94 electron volts and delta S 1 v equal to 1 kb, where kb is the Boltzmann constant. With these parameters, if we estimate the vacancy concentration at 900 degrees centigrade, it is about 2.5 times 10 to power minus 4. At 1000 degrees centigrade, it is about 5.2 10 to power minus 4, and at 1064 degrees Celsius, which is the melting temperature of gold, it comes out to be around 7.9 times 10 to power minus 4 side fractions. Okay. So, this was about the differential dialectrometry. The next technique that we are going to talk about is the residual resistivity measurement. As the name suggests, this technique relies upon measuring the resistivity of a sample and relating it to the vacancy concentration. Right. So, the resistivity of a metal basically has different contributions. Right. One is of course from the phonons or thermal vibrations of atoms, and the other one is from the defects which are present in the crystal lattice of the metal. So, the first contribution is rho t, and the defects include vacancies, grain boundaries, dislocations, impurity atoms, and other defects. Right. So, since we are interested in vacancy measurements, so let us separate the vacancy contribution and the contribution due to other defects. So, let us call the contribution from vacancy to be rho v, and rho d is because of the other defects, including grain boundary, dislocations, etc. Now, if we can measure the resistivity of the same piece of metal in two different conditions such that the rho t and rho d is constant in the two conditions, but only rho v changes, then all the change in the resistivity is only because of the change in vacancy concentration. Right. So, we basically want to make delta rho equal to delta rho v, and this is proportional to delta x 1 v. Okay. So, how do we go about this? So, we have to first take a piece of metal and equilibrate it at a lower temperature and measure its resistivity. So, the first step is measure rho 0 at T 0, then hit the metal piece to a higher temperature T, equilibrate at T, so that the equilibrium vacancy concentration at temperature T is achieved, and then quench from T to T0. Now, if the grain boundary and dislocation density is not affected, then essentially we get back the sample at temperature T0 with quenched in vacancies from higher temperature T. Right. So, whenever we are doing a heating or cooling, as the temperature changes, system tries to achieve the equilibrium vacancy concentration, and this is done by diffusion of vacancies to sources or sinks. Right. If the vacancies have to be created, there are sources. So, these grain boundaries, dislocation and surfaces act as sources. So, for example, if there is a dislocation and if a vacancy has to be created, an atom from the crystal will jump into the dislocation, and a vacancy from the dislocation will make a reverse jump and will be introduced into the crystal, and this is the way a vacancy is created. Similarly, grain boundaries or surfaces can act as sources of vacancies when we heat the sample to a higher temperature. Now, when the equilibration starts at higher temperature, you can understand the vacancy concentration near the defects would be very large, but the equilibrium wants that the vacancy concentration should be uniformly distributed throughout the bulk of the crystal. So, the vacancies then have to diffuse from there to the other parts of the lattice, and so the equilibration will take some time. Similarly, when the temperature is reduced, the extra vacancies, the vacancies which are in excess of the equilibrium concentration at that temperature, have to be gotten rid of, and that occurs by diffusion of these vacancies towards the defects. Now, the same defects will now act as sinks. That means that the creation or annihilation of vacancies requires time, because it is driven by diffusion. By quenching from higher temperature T, we are not giving enough time to vacancies for annihilation, and so the excess vacancy concentration will be retained at the lower temperature. Okay. And the fourth step here is to measure rho again at T0, right. But the difference between step 1 and step 4 is that in step 1 this was the resistivity of well annealed sample, step 4 the resistivity is of quenched sample. Now, if the density of dislocations and the grain boundary area remains constant, the only contribution to the change in resistivity is going to be from the change in vacancy concentration, because we are doing the measurements at the same temperature, rho T is also same, and then we can write this delta rho is equal to some constant A times delta x 1 V. So, how do we keep the grain boundary and dislocations constant? That is why it is important to start with a well annealed sample. The sample has to be first equilibrated at a high temperature, so that the grain growth takes place and the grain boundaries are well stabilized. There should not be any further grain growth or elimination of smaller grains during the subsequent high temperature heating. Preferably a large grain sample is used, so that there will not be much significant change in the grain boundary area. Similarly, the dislocations, the dislocation density will be minimized after annealing, but during quenching dislocations may be introduced. So, we have to take care that the dislocations are not introduced during quenching. So, we can try to avoid the introduction of new dislocations by first quenching it to a lower temperature, let us say to 100 degree centigrade, and then from there to the lower temperature T0. Now, this lower temperature T0 is typically sub-zero temperature, minus 70, minus 80 degrees Celsius, because at that temperature the contribution from thermal vibrations is going to be very low. So, the change in delta rho v is going to be prominent. Now, this delta x 1 v, again the difference between T and T0 is going to be very large. So, delta x 1 v can be approximately taken as equal to x 1 v at the quenching temperature T. And so, we can write delta rho is equal to A exponential delta S 1 v by k times exponential minus delta H 1 v by k T. And remember, this T here belongs to the quenching temperature. Remember, this T here denotes actually the quenching temperature. Now, with this technique, as you can see, we can measure delta rho from different quenching temperatures and plot it. Plot the logarithm of delta rho versus 1 by T. Again, we will get a straight line whose slope gives us the value of delta H 1 v. Okay. So, with this technique we do not get the absolute concentration of vacancies, because there is this constant A which we do not know, but by determining delta rho at different temperatures and plotting it against 1 by T, we can get to the enthalpy of vacancy formation delta H 1 v. Again, since A is not known, so from the intercept we cannot actually determine delta H 1 v. So, this is a simple technique, it does not give the absolute vacancy concentration, but we can get delta H 1 v based upon residual resistivity measurement. So, let us look into some of the literature data. I have shown the results from couple of papers here. The first one is from Bourassa and Lengler, who measured the vacancy concentration by residual resistivity measurement in pure copper, and they use the quenching temperature in the range of 750 to 1050 degree centigrade. You can see a nice straight line fitting is obtained, and they measured delta H 1 v to be 1.27 electron volt for copper. With this, if we determine x 1 v at the melting temperature of copper, it comes out to be around 1.4 times 10 to the power minus 4. If we take delta S 1 v to be 2 kb, again delta S 1 v cannot be measured by this technique. This is just what I have taken from other data. Another example is from the work of Klauske and Kaufman. They measured the residual resistivity in the temperature range of 500 to 950 degree centigrade. This was the quenching temperature in the gold alloy containing 1.2 atomic percent silver, and they obtained in this alloy delta H 1 v to be 1.01 electron volt. Again, if we calculate the vacancy concentration at 1064 degrees Celsius, which is the melting point of pure gold, it comes out to be around 4.3 times 10 to the power minus 4 side fractions. So, this was the second technique for vacancy measurement. The third one that I will talk briefly here is based upon positron annihilation. So, some of the radioactive isotopes emit positrons while they are decaying. These positrons are nothing but the antiparticles. They have the same mass as electrons, and they also have the same magnitude of charge as that of an electron, but the charge has the opposite sign of electron. These are positively charged particles. So, in a sense they are anti electrons. And when the positrons combine with electrons, they emit 2 gamma rays. Yeah. So, what essentially is done in this technique is the piece of metal is kept close to a radioactive isotope. The most commonly used radioactive isotope is sodium 22. This emits gamma rays of energy about 1.12 mega electron volts and positrons. So, the positrons will go into the piece of metal, and there they will combine with the free electrons of the metal and emit gamma rays of the energy about 511 kilo electron volts. Now, when these positrons go into a vacant site of the metal piece, there is an absence of core electrons in the vacancy, and so it will take time for the positron to combine with the electron. So, we say that the positrons are trapped in the vacant sites, and more the number of vacancies, more positrons will be trapped, and then the average lifetime of the positrons will increase with the vacancy concentration. And this is the principle which is used in measuring the vacancy concentration from the lifetime measurement of positrons. Okay, so, this was the third technique. So, we will stop here today. Thank you.